Topic 3.2, cross-tabulations and statistical significance.
Take one. We'll do it.
So, do you remember back a few weeks ago when we were talking about experiments, and there I presented 3 criteria that you need to hit to demonstrate causality. The first is that you have to demonstrate covariation, then you have to deal with time order, making sure your cause comes before your effect, and then you also have to deal with non-spuriousness. For your research reports, a lot of you are already thinking pretty clearly about time order, what comes first in time, and if it's reasonable to think that, your independent variable comes before your intervening variable, things along those lines, and you're already thinking seriously about sources of spuriousness. But also a number of you are thinking, how exactly do I actually get evidence for my hypothesis? How do I demonstrate covariation? This is what we're going to do next. So if you see in the overview, what we're going to cover in this first bit of this week's content is how we demonstrate covariation, or how we demonstrate covariance, how we create something called a cross-tabulation or a crosstab, how you interpret a crosstab, what you do to get statistical significance, the difference between something called type 1 and type 2 error, and then a really important stat that all of you are going to be using in your research reports, something called the chi-square test. So for things first, how do we demonstrate covariation? When we're demonstrating covariation, what we do is we ask 3 questions. The first question is looking at the degree of the relationship. So how strong is the relationship between the independent variable and the dependent variable? Do we see big differences? Do we see little differences? How strong is that relationship between the IV and the DV? What's the form of the relationship? Which values of the dependent variable are associated with which values of the independent variable? Is it positive? Is it negative? What's the form of the relationship? And then the last thing that we ask in terms of demonstrating covariation is statistical significance. This becomes important when we're dealing with sample data, like we would be with the Canadian election study or the American national election study. When we have a sample, we have to ask ourselves, can the relationship that we see in the sample, can the relationship that we see in our data, can we generalize that to the population from which the sample was drawn? So if you're using the American national election study, you want to be able to speak about Americans in general. You need statistical significance to do that. Similarly, if you're using the Canadian election study, you want to be able to say things about Canadians in general, and you need statistical significance to do that. But I want you to notice where the stats come in this process. We're talking about degree, so the strength of the relationship, and the form of the relationship, which we're eyeballing from the table. So we're coming in for the actual calculated statistic at the end of that process. The kicker for all of these is that the tests that we use to answer these questions depends on the level of measurement of both the independent variable and the dependent variable. So the higher your levels of measurement, the more high-powered and varied the statistical tests you can use and the techniques that you can use. But you really have to play to your lowest common denominator. So if one of your variables, either your independent variable or your dependent variable, is nominal, then you have to play to that level. You can only do the higher-powered tests if you've got everything measured at a higher level of measurement. So let's say we have nominal data. What do? Say we've got a nominal independent variable and a nominal dependent variable. How do we demonstrate covariation? We do this by setting up something called a cross-tabulation or a crosstab. Literally, you are tabulating across variables. On your screen, you can see that you've got a basic template for what a crosstab will look like. This just has a nominal independent variable, a nominal dependent variable. Both only have 2 categories. You can see the independent variable is in the columns, the dependent variable is in the row, and you can see that you've got totals kind of going all around. Those total rows and columns, they don't count for the total number of columns we have in a crosstab. We're really concerned about the total number of categories for the independent variable and the dependent variable. The blank spots where you can see like the intersection between independent variable category 1 and dependent variable category 1, that's called a cell. So each one of those little squares, like in between, in the middle of the table, those are all called cells. So to make a crosstab, we put the independent variable in the column, we put the dependent variable in the row. We label the categories of the independent variable across the top of the column, and we label the categories of the dependent variable across or down the rows on the left-hand side. There's a couple of other rules that I want you to keep in mind. Every crosstab has to have a title, and the title has to give some kind of substantive cue as to what's going on in the table. So you usually want to speak about like what the independent variable and the dependent variable is, usually something about the like something general that basically tells you what's in the table. And then you'll notice at the bottom left in italics, there's this source. And what you want to do is you want to give the source of the data set that you're using, which is why it says source, the data set I am using. So you would plug and play whichever data set that you were using there. Now, you'll also notice, and this is one of the reasons why we were starting to do recodes so early in tutorial, is that by the time you get to this point, you need to be really comfortable dealing with things like missing data. There's no space for missing data. There's no space for people who don't know how to answer the question, who refuse to answer the question. We need to recode them out. So here we're dealing with like the cleanest version of our independent variable and the cleanest version of our dependent variable. For your research reports, there's a reason why I've got the template here using 2 categories each. This is like the minimum that you're allowed to have. The maximum you're allowed to have is 3 categories. So you could have IV category 1, 2, and 3, but beyond that, your recodes have to be like capped at 3 categories for both your independent variable and your dependent variable. So if you're doing this with nominal data, and there are categories that you don't care about with nominal data only, you can drop categories.
Like it's hot.
So if you're looking at something like vote choice, and you are wanting to figure out how people voted, in 2019, you can drop the People's Party
Like it's hot.
because nobody voted for them. You could drop the Greens because nobody voted for them. If you're looking at elections outside of Quebec, obviously you're not going to be including the Bloc Québécois, things along those lines, right? And so only with nominal data can you just drop categories. If they're not relevant to your question, you can just chuck them out. Only for nominal data. Say it with me. You can only eliminate categories when you're setting up your crosstab when you are dealing with nominal data.
The 23.
So you've seen the basic template for a crosstab. Now I want to show you what it looks like when we actually start to put data in it. So on your screen here, you can see a table from the 2015 Canadian election. Here I'm looking at the gender, or at least women and men. So women and men and vote choice. I've restricted, so you can see from the table, the title says gender and vote choice in the 2015 Canadian election, bracket outside Quebec. So just as an aside, anybody who wants to study vote choice in Canada, you either need to look at it inside Quebec or you need to look at it outside of Quebec, but you can't do both at the same time. And the main reason why is because different parties compete. We don't have the Bloc Québécois outside of Quebec. And so given we've got different kinds of party competition, either you're looking at everybody but Quebec or you're looking inside Quebec, but not both at the same time. So here I'm outside Quebec. You can see that I've got vote choice as defined by party. I've got the Liberals, the Conservatives, and the New Democrats. Because vote choice is nominal, I've dropped all the parties that are extraneous or, receive too few votes to actually be useful in this context. And then I've got gender as categories with women and men. You can see I've got totals, and also you can see in the bottom I've got this source, CES 2015. This is the actual data from the 2015 election study. So recall how the basic thing that we want to do is to compare. And we want to compare the effects of the independent variable on the dependent variable. We're trying to see how, in this case, women and men, how their vote choice varies across the Liberals and the Conservatives and the New Democrats. Here you can see that I just have the actual counts of people. So there were 512 women who voted Liberal in 2015 in the Canadian election study, 299 women who voted Conservative, 186 men who voted New Democrat, things along those lines. Like was the case with frequency distributions, in a crosstab, we need these numbers, like you need the actual cell counts. This is what these things are, cell counts. But you also need relative frequencies in each one of these cells. So we need to be putting percentages into this particular crosstab. One thing that's worth noting is that the number one mistake that people make when they're building a crosstab is that they put the percentages in the wrong place, or they calculate them in the wrong place. So I want you to think for a minute about whether or not you would want to calculate the percentages based on the columns, in this case, across women and men, or if you wanted to do it across rows, in this case, across Liberals, Conservatives, and New Democrats. The key for this is to think about where the independent variable is. So when I'm looking at this, either it's going to be vote choice determines gender, which makes no sense, totally goofy, or it would be there's a gender gap in vote choice. So you could say women are more likely to vote to the left compared to men. Men are more likely to vote to the right compared to women. That particular hypothesis matches something called a modern gender gap, where in the past, women used to be more conservative than men and used to vote or support more conservative, often religious parties. And in places like Canada and the United States, this started to switch in the mid-20th century, and it's kind of stayed there. So in this case, the hypothesis would be women are more likely to vote to the left than are men, presumably supporting, say, the Liberals or the New Democrats more than the men would. Men, if they're voting to the right, would be more likely to support the Conservatives. So where do we put the percentages? In the columns or in the rows? If you said rows,
Another 400 meters at least.
you would be wrong,
Over here!
because the dependent variable is in the rows. You always want to build your percentages where the independent variable is. So cell percentages must be calculated in terms of the total number of cases in each category of the independent variable. So this is why I give the advice of always putting the independent variable in the columns. It'll just make your tables easier to read. It'll just make it easier where you're going to place it. Put your independent variable in the columns and then calculate percentages based on the columns. So always, always, always calculate percentages based on where the independent variable is. And to keep it easy, just always put your independent variable in the columns and then just run column percentages and you'll be fine. Okay. So now you can see on your screen, we've got a more complete version of this crosstab where we've got, again, the title. So we're looking at gender and vote choice in the 2015 Canadian election outside Quebec. And we've got the actual counts that we had before. And then in brackets, we've got percentages. And you can see if you read down the column, it sums to 100% at the bottom of each column. And then if you look at the row at the end of each row, it doesn't sum to 100%, right? This gives us the cue that we are creating our percentages in the correct place. We're doing them in the column where the independent variable is. Now that we've got this, how do I interpret this? I've got this table here. Now you know how to set it up. You've got the title, everything's labeled. You've got the cell counts, you've got the cell percentages. They're all calculated across the independent variable in the correct spot. Amazing. But if you're sitting there and just being like, how do I interpret any of this? How do I make any sense of it? Here's the clue that you need. If the independent variable is in the column, what you want to do is look across the gap of the column. So you're going to want to compare the percentage of women, in this case, who voted Liberal, compared to the percentage of men who voted Liberal. So we always interpret a crosstab by comparing categories of the independent variable, to use textbook speak, in terms of the percentage of the distribution of the dependent variable. This is just like saying, is there a gap in the proportion of the dependent variable across the columns, or across the columns of the independent variable? The bigger the gap, the stronger the relationship. So in this case, if my hypothesis is that women are more likely to vote to the left than are men, I would be looking at the left-leaning parties here. So I'm looking at the gap between women and men. For liberals, I've got women at 51%, I've got men at 43%. Quick mental math tells me that's a gap of 8 percentage points. Not 8%, 8 percentage points. If I'm looking at the NDP, though, I don't have a gap. So vote choice is one of these ones where it's a little bit tricky because, like, I had the hypothesis in this one cues that I should be seeing a gap in a gender gap in vote for both parties, and I really only see it for one but not the other. If I were to rephrase the hypothesis and say men are more likely to vote conservative than women, here I've got a 7 percentage point gap where you've got 37% of men who had voted conservative compared to 30% of women. The point is that the first thing that you need to do when you're trying to demonstrate covariation, the first thing that you need to do when you're writing up your research report, when you're actually doing the analysis, is you need to talk me through what you see in the table. You have to talk about the gaps across the columns. So here I see an 8 percentage point gap between women and men in terms of their propensity to vote Liberal. 51% of women in 2015 voted, according to this sample, voted Liberal compared to 43% of men. So this is in the direction of the hypothesis, right? In general, when we're interpreting crosstabs, there are 4 questions that we ask, or 4 things that we look for. The first thing is we look for, are there differences in the distribution of the dependent variable for different categories of the independent variable? So in this case, we're just looking at the gaps across the columns, just like we had just done in that example, right? Here's the thing. If your dependent variable only has 2 categories, only interpret the row that is named in your hypothesis. The other row is going to be the mirror image, which means that you're just going to literally repeat yourself, but backwards. So save yourself the time, save yourself the space to say other smart things in your research report. And really, if your dependent variable only has those 2 categories, just interpret the one that you've named in your hypothesis. So here, the first thing that you're going to do is you're going to talk about the differences in the distribution of the dependent variable for different categories of the independent variable. The first thing that you're going to do is talk about gaps across the columns. Okay. The second thing that you're going to do is you're going to compare the percentage differences with your hypothesis. So do you see the gap in the direction that you expected? In our example, we do. We see women are more likely to support parties of the left, men are more likely to vote conservative. And so we need to confirm that we're actually going in the direction that our hypothesis stated. And then we're also looking at the magnitude. So the larger the gap, the stronger the relationship. The third thing that we ask, again, is if there are differences, are they consistent with the hypothesis? And then and only then do we bring in a statistic. If the data come from a sample, could the differences that we see in the table, could differences that large as what we see in the table, have occurred by chance? So I want you to be really clear about the sequence in which you do this. You eyeball the table, you read the table to find gaps across the columns. You compare this to your hypothesis. Is this in the direction that I expected that it was going to be based on my hypothesis? How big are the gaps? Am I getting a cue that the relationship is strong or is it weak? So you're talking about the table, you're reading the table. Put this in your notes immediately and refer back to it when you're writing up part 2 of your research report. You need to talk about the table before you jump to a statistic. For every one of your tables, I want to see a paragraph explaining and answering those 3 questions. What are the gaps? How big are they? Are they consistent with your hypothesis? Then, and only then, once you've done that, do you turn to statistics.